I think we continue recording. Okay, let's continue with our explanation. Can you hear me, people? Can you hear me?
Yes, doctor.
Somebody answer me, please.
Yes,
Okay,
doctor.
can you see my full screen? Can you see my full screen?
Yes, doctor.
Yeah, it is full.
Okay, okay. So let's continue with the next topic, which is some statistics concepts, basic concepts. Okay. So, what is a random process? For example, Mr. Jimenez, if somebody says that you have to work with a random process, what comes to your mind? Mr. Jimenez?
Yes, doctor, can you hear me?
Yeah, I can hear you. Go on.
What's the
What is a random process for you? I mean, what comes to your mind? No? Mr. Ramon?
initial conditions?
Go on, Jimenez, go on.
We need the initial conditions.
Uh-huh. Don't read,
No,
don't read.
the function to approximate.
No. Statistics here. In an experiment, that's typical, right? You do an experiment and repeat it, and you get a different answer. But man, I'm doing the same beam, I'm applying the same load, but the strain is different. I know, there are so many things that you can't control. So the response is not exactly the same, it's close, but not exactly the same. So that's random, because you cannot assure that you are going to repeat the beam experiment and you are going to get the same result. It's going to be close, but it's not going to be the same. Exactly, never. And here you have another term which is very important for us, is probable. Okay, probable. Okay, so you repeat this 10 times, but yeah, some of the results are like packed around a certain value. And you can see that if you suspect the response to be in this region, yeah, it's likely that you are right. And the next time you do the experiment, you're going to have something in that order. Okay, so two things here. First, never are going to be the same. And second, yeah, there are regions where you can expect more likely to be the result. And this likelihood is what we call probability. And that's what we need in order to express or describe one of these processes, okay? This is something that we need to work with, is what we call an ensemble, right? An ensemble is a group of time registers. So here, in each one of these signals, this is time, this is time, this is time. But we have several measurements of the same parameter. And as we say here, okay, everything that we can control is the same. Everything that we can control is the same. But still, you see that there are some differences, okay? Okay, that's what we call an ensemble. It's like a group of time registers, okay? Now, let's see what we can do with this information, okay? So this is our example. Now, what we are going to do is we can take a certain time, okay? And we're going to see what information we have from each one of these signals at the same time, okay? For example, let's call it Ti. So this is Ti. So we have one value here, one value here, one value here, one value here, and one value here. Let's see what we have. So what we can do is we can do a zoom, right? And this is what we see, okay? This is a signal that you see here. It's there with a zoom. So what we can do is we can take the scale and break it into regions, okay? Into intervals. Now, in this case, this is the length of the interval. So we can split it into more and more in the positive and also in the negative side. Now, each one of these intervals is what we call a class. I'm sorry, this interval is defined using this size of the interval. Now, and if we want to put a name on each one of these intervals, we call it with the mean value of the interval. So this is the mean value between this and that value. And this is what we call the class. So Zi star is the mean value in this interval. It's like the name of this interval. So we can go up, so the class will be higher. We can go down, the class will be smaller or lower. So what we can do now is see, okay, in this case, this value, the second signal is like this one here is in this class. I'm sorry, in this interval. Okay, so what we have to do now is we're going to make an accounting. We're going to see how many of these values of each one from each one of these signals lie in each one of these intervals, right? And this is what we call an histogram, a frequency histogram. So we have the number of interval. This is the class of each one of them. And this is the number from each one of these signals that at time ti, okay, each one of these signals is in each one of these intervals. So for example, we know that from these results that 71 of these values are in the interval 2. And the interval 2 has a class of minus 147 meters. We add all of these, we have a total of 7,201 measurements. So this ensemble has 7,200 of this register. That's a lot of information. Okay, now we can go on and we can, okay, what is the chance? What is the chance, for example, that you pick one of these and that value is in this range? What is the I don't want to use the word probability, but that's the word that I'm going to use in a few seconds. What are the odds that I take one of these values and it's in this case in the fourth interval? Well, it makes sense to divide 90 by the total. And that's what we call the probability. So the probability that you take any one of these results and that result is in this range, in this interval, is this quotient. Is the number that about so many observations were in that interval divided by the total number of measurements. Okay, that's probability. Remember, when we defined a random process, we said, okay, they are more likely that the result will be in this or that area. And you see immediately these numbers are larger. That means that according to these observations, it's more likely that we're going to have a result in these intervals than in this one here. That's very important for us. Okay, now, what's the problem with this? The problem with this is that we have selected a certain size of the interval, okay? And you ask, what would happen if I had done this with a different size of interval? Larger or smaller? Well, in general, the results are going to change, okay? So we need another measure so that it doesn't depend on the size. And that's what we define it, what we call the probability density function, okay? So we said, okay, this is going to be equal to the probability density function multiplied by the size of the interval. Okay, so this is density. For example, you have mass. That's mass, right? If you define it mass per unit volume, that's density, mass density. It's per unit something. So that is independent of the size of the mass that you took at the beginning. Something like that, it's here. So probability density function is probability per unit width of interval. Okay, now, we have to be careful, please, because in general, we express this as large P and this as little p. If you're gonna get confused, yeah, don't pay attention to that, but please, I am the one who grades your work. If I think that that's a little p, I don't care what you say. That's a little p, that's a little p for me. Please be careful with that. If you want to express large p, write it large. You want a small density, well, write it as small. Okay? Please help me. And now this has a geometrical interpretation using differential calculus, right? If we plot here in the ordinates, right, we plot the density. See, if you take this delta to the left-hand side, this what it's going to give you the density. See, you have it here, and here I have the function or the variable, right? Then this area here is going to be equal to this times the width of this rectangle. And the width is going to be m divided by n, which is the probability. So basically, that's the relationship between those two, okay? So the area under the probability density function is the probability, okay? That's something that you recall from the very beginning, okay? That's what we have. Now here, there's something which is very important, is units, okay? Remember, this is engineering, okay? In engineering, we care about units. What are the units of probability, Mr. Galarza? What are the units of probability, Mr. Galarza?
The probability is a dimensional, doctor.
Mm-hmm.
And the
Exactly.
other...
But the probability density function has units of 1 over the variable. Okay, so for example, if you want to work with the elevation, okay, so the probability density function would be 1 over meters. If you want to work with the bending moment on the midship section of a ship, in that case, the probability density function will be 1 over pascals, etc. Please be careful, okay? You have seen so many times with me classes, right? And every time I insist on units, okay? So if I ask you to calculate this or that, remember, in case of a density function, probability density function, you have to include the units. It's dimensional. Okay, and we can go, when we can take many of these time registers, okay? So we can get delta zeta to be very small. And in that case, instead of this thing, we are going to have in the limit, we're going to have a continuous curve. That's what we see here. Okay, this is a continuous function, right? And according to the definition, the area under the probability density function is going to be the probability. So this is going to be the probability that, in this case, X is between A and B. Okay, that's something that we know, but it's just a reminder. Okay, this is just a review. Now, this is a big problem because we're saying here is that we need N to be very large, right? In the previous slide, I mentioned that it was what, 32,000 values? Man, that's a lot for a number of registers. So what we can do is this: we can include an assumption, and the assumption is that the process is going to be stationary and also ergodic. Okay, so let me go back here. I did this process for a certain time ti. Okay, what would happen if I do this? I take another time tj, or another time ek. Okay, of course, this table for the frequency histogram is going to be a little bit different, but in general, it's exactly the same. We're going to assume that it is stationary. That means that if we make a cut at ti, tj, tk, or any time, the results is going to be the same. Okay, that's one thing, stationary. And the other thing is that we're going to assume that it is ergodic. Okay, this is a new word probably for you. That means that instead of having an ensemble and take at a certain time one value for each one of the time registers, which is a very extremely large process, we take one signal and we integrate in time. And the results, statistics, parameters are going to be the same. Okay, there are certain random processes related to ship dynamics, which are not ergodic. Okay, but in general, in our case, we're going to assume that it is so. Okay, so we're going to assume that it is stationary and it is ergodic. And once we assume that it is ergodic, that means that with one single well-measured register, we can get a lot of information for our calculations. Okay, in general, of course, it is always recommended to do more than one signal, one measurement, and then from there we can start going and make a comparison and things like that. But theoretically, with one single register, long enough, that's enough for you. So instead of taking one value, you take the integration in the time direction. For example, okay, I developed this this register in the computer, and from there I use this the blue from the histogram. Okay, and you see that the red here, it's kind of close. Okay, but that's basically the process that we follow. Okay, we did some measurements and then we try to fit one function that resembles, like very close to the histogram that we have measured. Okay, and in this case, the function that you are going to remind is what we call the normal distribution. Okay, so for you to remember that there are certain processes, random processes, which follow this distribution. Okay, so in this case, this is a distribution, this is a variable z, and we have two parameters, okay, mu and sigma. Okay, you remember that sigma squared is the variance, mu is the mean value, and the square root of that is the standard deviation. Okay, in a minute, we were going to recall the definitions of these parameters. So we take one single, get a histogram, plot it, and then what we can do is we can try to fit a curve, and we can say that in general, to do future extra work, what we can do is we can assume that this process follows a certain rule. In this case, this is a normal distribution, okay, which is the most common one that we employ. You integrate that, Ms. Lopez, can you integrate the normal distribution? Ms. Lopez?
Yeah.
Can you integrate the normal distribution?
Yeah. No. I don't remember.
Ms. Pinkai, can you integrate the normal distribution? Ms. Pinkai, can you integrate the normal distribution? No, Ms. Pinkai had problems. Ms. Freire, can you integrate the normal distribution? Ms. Freire? No, the answer is no. There is no integral for that. Okay, what we can do is we can rely on tables. Okay, so if I want to give you an exercise on this in the evaluation, I have to add a table. You can use it to integrate it. Okay, so these things are not new for you. You studied these things. Okay, so please remind. Okay, now in this case, I calculated the mean value. This is the mean value, and this is the standard deviation. And with these two values, I plotted the red curve. It's close, meaning that for this function, very ugly function, we could think that we can express these probabilities assuming that it is normal distributed, okay? So once we have this, we can say, okay, what's the probability that we are below 2 meters or between 0 and 2? Okay, well, in that case, what we have to do is we can integrate this area, the probability that we are between 0 and 2. But to do this integration, we have to rely on tables because this function does not have an integral. People, don't remember this? Go back to your class notes. That's something that you studied already. Okay? Those tables, you have to use a standard variable. Does anybody remember the value of the standard? Some people call it Z. Standard normal? No? Okay. In 2 weeks, we have an evaluation on this, so you better review it. Okay, some other concepts here. For example, if we have a function zeta of time, okay, we can integrate it in a certain interval and divide it by the length of the interval, and that by definition is the average. This is that you need to have the function zeta of time. In the real world, most of the time, we don't have this function. What we have is a group of these functions, right? Like, for example, results from measurements from an ensemble or register in time, something like that. But we do not have the function zeta as function of time. In that case, what we can do, for example, this is something that we have to do, okay? The expected value, that's a nice approximation for the mean. By definition is this. And you is multiply by this is the probability. Okay, and this is probability that you are in the range between plus and minus dz over 2. You multiply by z, that's the first moment, and that allows you to calculate the expected value. If you have the result from an histogram or something like that, what you can do is you can, instead of integration, you can replace it by a summation. And you can identify that this divided by that is also the probability. So it's P times Z. Here is P times Z integral summation. You see the equivalence of these two processes. Okay? Mean squared, right? For example, in the case of, we see here, okay? This is 0. We have values in the positive or in the negative side. If we calculate the mean, probably the value will be very small. But you're interested in these values here because we have a large wave, but the mean is 0. The problem is that if you add positive and negative sides, the result is going to be very small. So what we need to do is to add not only the positive, but also take the negative and also contribute in that summation. And that's obtained when we square the function. Okay, so we squared, integrated in an interval long enough and divided by the length of the interval. And that's what we call the mean square. So it will be the mean of the square. That's a mean square. Okay, if you know the function zeta in time, so you can integrate it. If you do not know, then what we can do is we can propose a parameter to estimate that. And this is the parameter to estimate the mean square. So this is the way to calculate it. And if we know an histogram, this is the way we can calculate it. And again, m divided by m is equal to p times dz. Z squared, c squared. So this is like a discrete summation. This is a continuous summation, which is an integral. So this is the mean square. Okay, mean square, units of length or z squared. That's the variance. Okay, so it's always a good idea, right, to know if you have a mean value, how far we are away from the mean, right? For example, in a class, okay, we have a mean value. How much is the mean? Okay, 65, but what's the variance? And the variance will tell you how much we have to the right and to the left. If we have a class with an average of 75 and a variance of 5, that means that mostly people are in the range between 70 and 80. So that's a very good, that's a uniform class, very good one. The problem is that, for example, I have an average of 70, but the standard deviation or the variance is very high. That means that, yeah, the average is here. I have a very good student here, but also I have a low student down here. That means that that's not a very good class. I'm not doing a good job. Because maybe I'm motivating these people here. Yeah, but these other people are behind. And I should try to drag them so they can go on and recuperate. Okay, so that's the way to evaluate this, interpret this variance. You can this square and integrate, and this is the result. Okay, so the variance, which is equal, it's in the, you can No, it's not interpretation. It's the expected value of the difference between the mean, this is the mean, and the function, and the variable, I'm sorry, squared. It's like a measure of the spread, okay? It's equal to the mean squared minus the mean raised to the second power. Careful with the words. This is the mean squared. This is the mean raised to the second power. In some cases, this is zero. The mean is zero. For example, the wave elevation, the mean is basically zero. So in that case, the variance is equal to the mean squared. There is the autocorrelation function, okay? And you see that I have a function here, evaluated at t, and I multiply by the same function, but at the time increases by this amount, tau. So it's, I'm here, and I'm trying to see what's the relationship of my value with the value that you are going to have up here. So you see here and here, see here and here, the two. How is the relationship between them? If you had, okay, in there, in the function, a very strong harmonic, in that case, the period, we can identify that. Why not? Because when you are here and you are trying to see the relationship with the time, which is equal to this one plus the increment, then the two functions will go like this. So in general, that will give you a large increment. Okay, that's what we're trying to show here. Okay, so for example, you see what's the relationship between here and here, and you keep going to the right. Now you are here and try to see what's the relationship of this with that. For example, this is positive, this is negative. So the result is negative. This is positive, negative, this is positive. The result is negative. So in that case, it starts in summing up. But in some cases, it's possible that this product is positive, then it's negative, then it's positive. The result is going to be very small. But when you have a period at tau, the result of this integration will give you a good value. Then we have to divide it by the time of integration, and the result is what we call the autocorrelation. Why auto? Because it's being how it is correlated to himself, right? So I correlate with myself. That's what this function is called, the autocorrelation. And for when we have the presence of harmonics, this autocorrelation will have a good value when you have at the value of the period of this harmonic. We're very close. Give me a couple of minutes, please. If we evaluate this at tau equal to 0, if this is 0, then you're going to have z squared. So this is going to be the mean squared. This is what we have here. Okay. Now, in general, here, this is mean squared, right? Now, if we get the square root of this is what we call the root of the mean squared, what we call RMS. So the RMS would be the square root of the mean squared. And if we raise to the second power, we cancel this, and this is what we get. Okay, so the autocorrelation for tau equal to 0 is equal to the mean squared, and it's equal to the RMS squared. And finally, oh man, let me erase this. Sure, nothing of this is new for you. This is just a review. Okay. Now, this is this one here. Now, if one this equal to that, in that case, we need this to be 0. This is what we're saying here. If the random variable has mean value, the expected value of this variable is 0, okay, in that case, this is equal to that, and that's equal to the variance. Okay, that's it's useful to recognize. Okay, people, is there any questions so far? So tomorrow, Giovanna, we're going to start at about 8:30, right, Giovanna?
Yes. Can you repeat?
8:30, right? 8:30.
Tomorrow, yes.
Okay, yeah. So, yeah, 8:30, more or less, okay? If you come late, yeah, we're not going to wait for you, okay? We're going to start with the people who are at 8:30, and then we can go on, okay? If you come late, if you want to repeat the experiment, yeah, you can do it. You can your own values. Otherwise, we can develop the experiment with the people who were there, and then we're going to share it with everybody else, and then that's it. Okay, now, next, the experiment that we're going to develop tomorrow, that's going to be the class for Tuesday. So on Tuesday, there's going to be no class, right? But at night, I'm going to be available to you, right? So if you have problems with the homework or the analysis of the signals, yeah, I'll be available to you. Ian, okay? Yeah. Any other question, people?
The next week is the quiz 3? No.
I'm sorry, I didn't get it.
The next week is the quiz?
No. So this is the second week, right? Next week is the third one. And then in the next one, we're going to have the evaluation.
In the evaluation, we evaluate the chapter 4 and 5.
Yes, yes. What we can do is this, if you want. In a week, okay, outside the city, the problem is that it is possible that I can connect to the internet, but it is possible that I have some interruptions. Okay, so what we can do is we can you have to review the class notes, and I'm going to give you the last Tuesday a short review of that, and that's it. Probably it's not going to be long enough to do all the material for this chapter. But don't worry, I'm going to be consistent. I'll try to be give you in the evaluation. I'm going to give you questions which are related to the material which can be covered up to the next Tuesday. Yeah, definitely. This is just a review about the statistics. That's all what it is. So don't come and cry into me. This is just a review. Okay, is there any other question, people? Any other questions? Oh, then I'll see you
Sorry,
tomorrow.
Doctor, when are
Yeah.
you going to do the next test?
On the 4th week, Thursday.
Okay, thank you, Doctor.
Don't ask me for the dates, okay? Because yeah, this is the second week. Next, of course, is the third, and then comes the week of the evaluations on Thursday in the afternoon. On Friday, we will have basketball. No more questions? Okay, Giovanna, is there no more questions, people? Then see you tomorrow. Giovanna.